Where is Earth's submoon? Can moons have moons? This simple question, asked by the 4-year-old son of Carnegie's Juna Kohlmeier, started it all. Not long after this initial bedtime query, Kohlmeier was coordinating a program at the Kavli Institute for Theoretical Physics (KITP) on the Milky Way while her one-time college classmate Sean Raymond of Université de Bordeaux was attending a parallel KITP program on the dynamics of Earth-like planets. After discussing this very simple question at a seminar, the two joined forces to solve it. Their findings are the basis of a paper published in Monthly Notices of the Royal Astronomical Society. The duo kicked off an internet firestorm late last year when they posted a draft of their article examining the possibility of moons that orbit other moons on a preprint server for physics and astronomy manuscripts. The online conversation obsessed over the best term to describe such phenomena, with options like moons and mini-moons being thrown into the mix. But nomenclature was not the point of Kohlmeier and Raymond's investigation, although they do have a preference for submoons. Rather, they set out to define the physical parameters for moons that would be capable of being stably orbited by other, smaller moons. Planets orbit stars and moons orbit planets, so it was natural to ask if smaller moons could orbit larger ones, Raymond explained. Their calculations show that only large moons on wide orbits from their host planets could host submoons. Tidal forces from both the planet and moon act to destabilize the orbits of submoons orbiting smaller moons or moons that are closer to their host planet. They found that 4 moons in our own solar system are theoretically capable of hosting their own satellite submoons. Jupiter's moon Callisto, Saturn's moons Titan and Iapetus, and Earth's own moon all fit the bill of a satellite that could host its own satellite, although none have been found so far. However, they add that further calculations are needed to address possible sources of submoon instability, such as the non-uniform concentration of mass in our moon's crust. The lack of known submoons in our solar system, even orbiting around moons that could theoretically support such objects, can offer us clues about how our own and neighboring planets formed, about which there are still many outstanding questions. Kohlmeier explained. The moons orbiting Saturn and Jupiter are thought to have been born from the disk of gas and dust that encircle gas giant planets in the later stages of their formation. Our own moon, on the other hand, is thought to have originated in the aftermath of a giant impact between the young Earth and a Mars-sized body. The lack of stable submoons could help scientists better understand the different forces that shaped the satellites we do see. Kohlmeier added, and, of course, this could inform ongoing efforts to understand how planetary systems evolve elsewhere and how our own solar system fits into the thousands of others discovered by planet-hunting missions. For example, the newly discovered possible exomoon orbiting the Jupiter-sized Kepler 1625b has the right mass and distance from its host to support a submoon, Kohlmeier and Raymond found. Although, the inferred tilt of its orbit might make it difficult for such an object to remain stable. However, detecting a submoon around an exomoon would be very difficult. Given the excitement surrounding searches for potentially habitable exoplanets, Kohlmeier and Raymond calculated that the best-case scenario for life on large submoons is around massive stars. Although extremely common, small red dwarf stars are so faint and their habitable zones so close that tidal forces are very strong and submoons, and often even moons themselves, are unstable. Finally, the authors point out that an artificial submoon may be stable and thereby serve as a time capsule or outpost. On a stable orbit around the Moon, such as the one for NASA's proposed Lunar Gateway, a submoon would keep humanity's treasures safe for posterity long after Earth became unsuitable for life. Kohlmeier and Raymond agree that there is much more work to be done, and fun to be had, to understand submoons, or the lack thereof, as a rocky record of the history of planet-moon systems. Sean Raymond maintains a science blog, planetplanet.net, where more details and illustrations, including a poem he wrote about the article, can be found. This research was supported by a grant from the Agence Nationale pour la Recherche, the NASA Astrobiology Institute's Virtual Planetary Laboratory-led team, and the National Science Foundation. Scientists find increase in asteroid impacts on ancient Earth by studying the Moon. An international team of scientists is challenging our understanding of a part of Earth's history by looking at the Moon, the most complete and accessible chronicle of the asteroid collisions that carved our solar system. In a study published today in Science, the team shows the number of asteroid impacts on the Moon and Earth increased by 2 to 3 times starting around 290 million years ago. Our research provides evidence for a dramatic change in the rate of asteroid impacts on both Earth and the Moon that occurred around the end of the Paleozoic era, said lead author Sarah Mazrouet, who recently earned her PhD in the Department of Earth Sciences in the Faculty of Arts and Science at the University of Toronto, U of T. The implication is that since that time we have been in a period of relatively high rate of asteroid impacts that is 2.6 times higher than it was prior to 290 million years ago. It had been previously assumed that most of Earth's older craters produced by asteroid impacts have been erased by erosion and other geologic processes. But the new research shows otherwise. The relative rarity of large craters on Earth older than 290 million years and younger than 650 million years is not because we lost the craters, but because the impact rate during that time was lower than it is now, said Rebecca Gent, an associate professor in U of T's Department of Earth Sciences and one of the paper's co-authors. We expect this to be of interest to anyone interested in the impact history of both Earth and the Moon, and the role that it might have played in the history of life on Earth. Scientists have for decades tried to understand the rate that asteroids hit Earth by using radiometric dating of the rocks around them to determine their ages. But because it was believed erosion caused some craters to disappear, it was difficult to find an accurate impact rate and determine whether it had changed over time. A way to sidestep this problem is to examine the Moon, which is hit by asteroids in the same proportions over time as Earth. But there was no way to determine the ages of lunar craters until NASA's Lunar Reconnaissance Orbiter (LRO) started circling the Moon a decade ago and studying its surface. The LRO's instruments have allowed scientists to peer back in time at the forces that shaped the Moon, said Noah Petro, an LRO project scientist based at NASA Goddard Space Flight Center. Using LRO data, the team was able to assemble a list of ages of all lunar craters younger than about 1 billion years. They did this by using data from LRO's Diviner instrument, a radiometer that measures the heat radiating from the Moon's surface, to monitor the rate of degradation of young craters. During the lunar night, rocks radiate much more heat than fine-grained soil called regolith. This allows scientists to distinguish rocks from fine particles in thermal images. Gent had previously used this information to calculate the rate at which large rocks around the Moon's young craters, ejected onto the surface during asteroid impact, break down into soil as a result of a constant rain of tiny meteorites over tens of millions of years. By applying this idea, the team was able to calculate ages for previously undated lunar craters. When compared to a similar timeline of Earth's craters, they found the two bodies had recorded the same history of asteroid bombardment. It became clear that the reason why Earth has fewer older craters on its most stable regions is because the impact rate was lower up until about 290 million years ago, said William Botke, an asteroid expert at the Southwest Research Institute in Boulder, Colorado and another of the paper's co-authors. The answer to Earth's impact rate was staring everyone right in the face. The reason for the jump in the impact rate is unknown, though the researchers speculate it might be related to large collisions taking place more than 300 million years ago in the main asteroid belt between the orbits of Mars and Jupiter. Such events can create debris that can reach the inner solar system. Gent and her colleagues found strong supporting evidence for their findings through a collaboration with Thomas Gernon, an Earth scientist based at the University of Southampton in England who works on a terrestrial feature called kimberlite pipes. These underground pipes are long extinct volcanoes that stretch, in a carrot shape, a couple of kilometers below the surface, and are found on some of the least eroded regions of Earth in the same places preserved impact craters are found. The Canadian Shield hosts some of the best preserved and best studied of this terrain, and also some of the best studied large impact craters, said Mazrouet. Gernon showed that kimberlite pipes formed since about 650 million years ago had not experienced much erosion, indicating that the large impact craters younger than this on stable terrains must also be intact. This is how we know those craters represent a near-complete record, Gent said. While the researchers weren't the first to propose that the rate of asteroid strikes to Earth has fluctuated over the past billion years, they are the first to show it statistically and to quantify the rate. The findings may also have implications for the history of life on Earth, which is punctuated by extinction events and rapid evolution of new species, said Ghent. Though the forces driving these events are complicated and may include other geologic causes, such as large volcanic eruptions, combined with biological factors, asteroid impacts have surely played a role in this ongoing saga. The question is whether the predicted change in asteroid impacts can be directly linked to events that occurred long ago on Earth. The findings are described in the study Earth and Moon Impact Flux Increased at the End of the Paleozoic, published in Science. Support for the research was provided by the National Science and Engineering Research Council of Canada, NASA's Solar System Exploration Research Virtual Institute, and the Natural Environment Research Council of the United Kingdom.